Hi there and welcome back. This is DB2, still our discussion on indexes. So we are still in chapter 10, in the midst of chapter 10, and something quite thrilling is lying before us in this video. And that is about index-only query evaluation. And well, it's all in the name. Really, we would like to perform query evaluation without using the table files, using only the indexes. Okay, so of course we were already used to look at the predicates inside our queries and check that all the columns that were mentioned in the predicates are indeed present in the indices. Otherwise, the index would not match the query. Now we are talking about something else. Now it's about all columns in the query mentioned anywhere, not only in the predicates, but also in all other expressions in the select clauses, anywhere. All columns that are being referenced, all columns C1 to Cn, they may be present in an index. Okay, so if this is indeed the case, then why access the table heap file at all? All the information would already be found there. No need to use the RIDs in the sequence set in the leaves of the index to dereference and get hold of the actual table rows in the heap file. Why would we do that? We would only find column information there that's not needed anyway. All the needed columns, or the needed columns of the query are already present in the index. Of course, what we would hope for is super speedy query evaluation. If only one heap file, namely the index heap file, which hopefully is small, is participating in query evaluation, then that promises quite some substantial performance gain. Okay. You might say, okay, well, I can enforce that. I can create multi-column, multi-dimensional indices, composite indices, concatenated indices, so many names for one concept. Anyway, so if I have a particularly important query in my workload and I look at the subset of columns that that it uses, then I could just create a composite index with all of these columns in their search keys. Well, you could do that, but that would of course lead to very wide search keys. And very wide search keys means very wide index entries in the inner nodes. Very wide index entries in the inner nodes leads to a reduced fan out, to narrower trees that are deeper, and that would be a pity. So some performance trade-off there. So in newer versions of PostgreSQL, and that is also found in other database systems, there's indeed a particular special create index command that is geared to support this situation and this idea of having very wide indexes, index-only evaluation indexes. Okay, in that particular version of the command, in the create index command, we would split up the set of columns, C1 to Cn. We would split it in two and only include the prefix of the columns, a subset of the columns, the first k of the columns. We would use these to organize the B+ tree and have them present in the search keys. Okay. So only k columns would be present in the search keys. Narrower search keys, narrower index entries, fan out increase. That's good. And all other columns, the columns ck plus 1 until cn, they would only be present in the leaves of the B+ tree, only in the sequence set. So we would indeed find the column values, the needed column values inside the index, right? But these predicates that are probably not being used in range predicates, not being used in predicates that could narrow down index search range, they are only present in the leaf pages, so that we can grab them there, collect them there, and use them to answer our queries, probably to perform some arithmetic expressions or whatever. all of these attributes or columns are only found in the sequence set. Okay, so narrow keys, but still the index would carry all n columns, and we could have the hope of index-only query evaluation. Okay, so to really drive home what I mean with index-only query evaluation, let's look at the next slide that contains some examples of such queries. Okay, so for this slide, let's assume that there is an AC index. So it's a composite index that has been defined in our system, okay, on the table index, the well-known table that we already know and love. And now we could look at the set of queries, the 6 queries on this slide, and then ask ourselves, hey, could this AC index support this particular query? This is the old question of whether the index matches the query, okay, and also whether the information present in the index is already sufficient to evaluate the entire query. So no need to access the heap file for table index at all. So let's look at the first query here. Okay, so it's using this particular range predicate here on the A column. The A column is a prefix of this composite index, so that would be a good match. We could use this range predicate here to narrow down the index search range in this composite index. All right, when we do that, we would at some point we would encounter the leaf level. The leaf level, the sequence set of our B plus tree, and in these in the index entries in the leaves, we would also find the C values. Okay, the C values would be present because this is a concatenated index. The C values would be present in all of the index entries. In the inner nodes, they have been no value in the inner nodes to narrow our search range, but they are present in the index. In the sequence set, we could just grab the C values there and, well, output them to produce the result of our query. No need to access the table heap file at all. How about the second query here? Well, it's using the C column to define the index search range. And, well, the C column is a suffix. It's not a prefix of our composite key here. So, using an index scan would actually not be super clever here. Well, we would have to search the entire sequence set, but we would find everything in the sequence set that is needed to evaluate this query too. All right, so regarding indexing search, it's probably no good idea to use the AC index, but we could have index-only query evaluation. We could enforce it in the system. If we force it to use an index scan, it would find everything needed to evaluate the query too there. Okay, so that would be an index-only query with, well, let us parenthesize it. It's, while this would be index-only. Okay, so how about this query? Query 3 has the A mentioned and the C mentioned, okay, in the predicate. This, of course, fits our composite concatenated AC index. We can use this to narrow down the indexing range and have a subset of the sequence set accessed only. And then in the rest of the query here in the select expression, we would only access the A and C attributes here. All of them are present in the sequence set entries in our B plus tree. This is index-only query evaluation that could be performed with the AC index. All right, and I think it's the same for this query. The range predicate fits. It's a prefix of the concatenated key. Okay, while I scan the subset of the sequence set that is relevant for this predicate, I could collect the C values from the index entries. No need to access the table yet. And well, of course, I could find the maximum C value that I see while I scan the subset of the sequence set. So this could be indeed index-only query evaluation. So a check mark there and a check mark there. How about this query? It's a group by query. Is this supported by an index at all? Well, if you think about how you would evaluate a grouping operation, and we will talk about this in the sequel of the course, then an order on the A values of this index table would be very helpful. All the rows that make up the rows of one particular group would be adjacent in this A ordering, and such an A ordering is provided by our B plus tree index in the sequence set. So indeed, using the index to evaluate the group by would make sense. Okay, all that we need to evaluate the rest of the query is present in the indexing entries, the A column, the C column. We could provide or compute the C sum while we scan the sequence set. So indeed, this could be an index-only query. And I think only this last query, the sixth query here, while it matches regarding its predicate, well, it refers to the B column, which is not present in the composite index. Okay, this of course doesn't mean that we cannot use the index. We can fully use it here. We can narrow down the index scan range and scan a subset of the sequence set only, but we would then need the RIDs. We would have to dereference the RIDs, peek into the heap file to collect the B values to compute the requested minimum here. So this would be not an index-only query, but it would be an index-supported query. It's just not the cool case where we can leave the heap file aside. Okay. So one caveat here, one caveat. If you recall our discussion of row updates and how they are implemented in some database systems, in particular database systems that implement multi-version currently control, and PostgreSQL is one of such systems, then you may recall that an update on a particular row and also a delete on a particular row does not lead to its immediate deletion or really removal from the pages and also from the indexes. Instead, what we do is we manipulate the xmin and xmax values of that particular row, the visibility time frame, the visibility timestamps that define in which time frame this particular row has been visible. Okay, so this is how deletion is, or update, row update is implemented in PostgreSQL and also in this entire family of database systems. It's very efficient to implement deletion and update like that. It also supports the concurrent access of multiple users that see different versions of the same row at different times. And all of this is very interesting, but it leads to one challenge for the index-only scan. The entries of these rows, the index entries for these rows that should be considered invisible from our viewpoint, are still being found in the indexes, in our AC index, for example. So the index-only scan will find these rows, okay? And only in the heap file, I will find the visibility information held in timestamps xmin and xmax. And this is, of course, bad news for our index scan. It means that, well, the entire purpose of the index-only scan is being defeated. If we perform the index-only operation, we would still need to check the heap file for visibility information. Any row that is not visible anymore would not be part of the query result anyway. So regardless of whether this row is being found in the index, it had to be removed or disregarded when we construct the query result. So this would defeat the sole purpose of an index-only scan. We would only need to check the heap file to check for row visibility, and that's true bad news. All right. To counter that and to address this challenge in PostgreSQL, what you will find is that each table's heap file comes with a so-called visibility map, a very compact data structure that encodes whether all rows in a page, there are many in general, whether all rows in that page are indeed visible. and there is no row that's currently being held on a page, but is indeed invisible. All right. So if all rows in a page are indeed visible, then an entry for that page in the visibility map will indicate so. And when we do an index-only scan, we will not check the heap file. We will check the much more compact visibility map of the heap file, check whether there are any rows affected by deletions or update. If this is not the case, if all the rows are visible to everyone on a particular page, then we can just leave the heap file page aside and do not access it at all. Only if the visibility map indicates, okay, some deletions and updates have been going on, you might be affected, then that index-only scan in this case would need to check the heap file and check for the visibility timestamps. So let's see a sketch of the entire situation here to make this fully clear. So this is what we are talking about. We are talking about three components. Okay, we are talking about, of course, the index, which would be above this line here. This is the index, and we would hope to have index-only evaluation using this particular index. There's, of course, the pages of the heap file, and each of these pages, this would be one page, another page, another page. All of these pages store many rows. And there's this third new item, the visibility map, abbreviated VM here on this slide. Okay, right. So in the original table state, when we have just populated the table, no row has been updated or deleted, all of these rows, all of its rows would be visible to anyone in the system. Okay, this is indicated by these bold rows that you see here on these pages. And indeed, the visibility map would indicate just this. It would indicate a bit of 1 for all pages. There's 3 pages here, so we would talk about only 3 bits here, a very compact representation. All 3 bits would indicate that all rows are indeed visible. Okay, so when we perform index scan in this index, we would enter at the root page, we would be led to the sequence set, which of course is doubly linked. We would scan the index set and find all the index entries here. Well, when we are looking at an index entry that is located on a particular page, all right, then we would check the bit for this particular page and check whether all its rows are indeed visible. If this is the case, there is no need to dereference these RIDs and access the true heap file page here. We would be content with all the information that is being found here in the sequence set, and we use that information to perform index-only query evaluation. If some rows on pages become invisible, either because of deletions or updates, for example, the T1 row here or the T3 rows here on the first 2 pages, they have been updated or deleted, then they are marked invisible regarding their Xmin and Xmax timestamps. Now, not all rows on these pages are visible. Some rows might be invisible to some transactions and to some users of the system. So we would set the visibility map bits to 0 here. Okay. As you can see, we have deleted or updated these rows on the pages yet, but the index has not been changed to reflect that. We still have 4 row ID pointers pointing to this page. We still have 3 row ID pointers pointing to this particular page. So an index scan this way would still indicate that there are 3 rows or 4 rows to consider, while the visibility map indicates no, this may not be the case. You have to check for row visibility on the actual page. And well, the index-only scan could still be an index-only scan, but it would need to check the heap file for row visibility in these cases. If we perform a vacuum operation, okay, the vacuum operation that we've seen so many times already, then these invisible rows would be collected if there are remain invisible for all users and transactions in the system. Now it would be time to really physically remove them from the pages and to also update all the index structures that point to these particular pages. And this is indeed the effect that we see here in the third part of the picture. The rows T1 and T3 have indeed been physically removed from their pages. Okay, all entries that remain here are indeed now visible for everyone. So we can set back the bits in our visibility map to 1. Perfect. Okay, we have also updated the entries, the index entries in the associated indexes. You see that only 2 or only 3 row IDs are now pointing to the contents of these particular pages. Everything has been brought up to date. If we evaluate the next query, the next potential index-only query in this situation, then no heap file accesses are necessary. That's what the VM, the visibility map, tells us. Okay, so that's quite the convoluted setup, but actually a very simple, idea that builds on a very compact data structure, this bitwise visibility map. So let's see whether we can indeed find this over on the PostgreSQL system. Okay, so here we are. Well, if you recall, our examples, they were built around a concatenated AC index. Right, and this is exactly what I'm trying to construct here. So I'm still talking about my regular indexed table, and I have removed most of the indexes there. All that's left now is this concatenated AC index. I've performed an analyze already. Let's perform a vacuum. You know that vacuuming is indeed irrelevant for this particular example, an index-only query evaluation. And now let's look at the situation that we find there. All that's left is the primary key index and our concatenated AC index that's relevant for our example here. Okay, very nice. What we will now activate is the PG_visibility PostgreSQL extension, which you probably can guess it allows us to inspect the contents of the visibility map of the VM data structure. All right, so let's do that. I think it's already activated in my database system. Yes, it is. Okay, and we could now check the visibility map for our index table. Okay, so we could check all the bits here. Each page of the index table is represented by its particular bit in the visibility map, because that would be 9,346 bits that we need to look at here. I just pick random 10 bits out of that. I pick random 10 pages and inspect their bits. This bit is indeed called all visible, which is the proper name for that bit because it indicates whether all rows on the page are visible to everyone. All right, so let's check that for just a random set of 10 pages. And we see, well, everything is visible for everyone on these random 10 pages. I could select another random 10 pages and I will see the same thing. The bit will be set to true or 1 for all of the pages because we have just performed a vacuum. Any rows that should have been removed have been removed. Indexes have been maintained. We are in a clean state. This is the perfect state for index-only query evaluation because we don't need to check any heap file pages. The visibility map tells us so. Okay, so let's see whether we can indeed see that. Well, here's a summary of all the pages that have their all visible bit set. It's indeed all the pages, the 9,346 pages. Okay, so now for query evaluation. Well, this should be an index-only query, right? So we have an AC index. The range that we define here is on a prefix of the composite key. Perfect. That could fit the composite index. We could use the index to evaluate this range predicate. All that we need to evaluate the rest of the query is just the CE columns. We sum them up. All of them are present in the sequence set of our composite index. This should be perfect for index-only query evaluation. Let's see what happens. Okay, query evaluated. Indeed, index-only scan. Index-only scan. So the heap file of the index table is completely left alone here. It's not participating in query evaluation at all. As you can see, 0 heap fetches. This is very nice. The index-only scan was prepared to maybe check the indexed heap file, the table heap file for row visibility, but it didn't need to do that. Heap fetches is 0 because the visibility map and all its set all visible bits saved us from doing that. All right, and this means quite a low number of page accesses that we have seen here. 42 page accesses only in index-only query relation. Or what we output here from the index-only scan is just the AC attributes, and that's sufficient to compute the aggregate. The aggregate here at the top, no need to access the heap file, perfect index-only query relation. Okay, I could now force this index-only scan. I could force it off only for this particular experiment, and then see how the situation changes. Okay, so this would be the same query that could be related with the index-only scan, but now cannot. Okay, so that's still an index-supported operation, but well, this is now a regular index scan because the index-only scan was forbidden. The predicate has not changed, the index condition has changed. More pages are now involved in this operation. More pages, of course, all the pages of the heap file have been accessed now, so there's quite a number of pages that we need to access here. Okay, so heap file accesses are being counted here, and only then we can perform the aggregate computation. All right, so that's bad. Let's quickly switch on index-only scan again. There you go. Okay, so well, now let's perform some updates, and these updates, they will lead to new versions of rows being created. Old versions of these rows are being marked as invisible. All right. You see that this predicate here in the update DDL statement will not affect all of the rows in the index table. It will affect well, every 150th row, and that amounts to 6666 rows that are actually being updated here in this statement. All right, so let's see. This is the update statement. Some rows are being obsolete now on the pages, and we see that if we check the visibility map summary of our index table, we had 9,346 entries. All pages had only visible rows, and that's different now. Okay, so on 2,679 pages, all of the rows are indeed visible. On all other pages, well, there is some rows at least, maybe many, maybe at least one row that would be considered invisible to some applications of the system. Our application, for example, our current terminal session. All right. So if we now perform this query again, you see it's the same index only, potentially index only query. Then let's see what happens. Okay. All right. So, well, the system still considers index-only scan to be a good alternative here, but the visibility map, as we've just seen, indicates that there's quite a number of pages for which we really have to check the heap file page for the current visibility information of the rows. And this leads to quite the number of heap fetches that we have to perform. We really have to look into the heap file, check the heap file for row visibility, and only then can make sure that a particular row is in the result of our index-only scan. So that really reduces efficiency here. These high number of heap fetches as indicated by a visibility map. We can even make the situation more worse and update even more rows. Now every 10th row is being affected by this update statement. And this means that I think all of the pages in our heap file are now carrying rows that are actually being deleted, or in this case updated. all of the pages are being affected now. Let's perform that. Every page is affected, says the comment, and I think that's true. Takes a while. All right. So all of the pages have invisible rows now, and I think we should see a 0 here. Right. So no page has been left alone. The index-only scan would need to check every single page for row visibility information. All right. So let's see how the system decides to perform this query now. This is the query again. It could be index-only query regarding our AC composite index, but if we perform this query, you will see that, well, the system has decided to not bother with visibility map information. It will just perform a regular index scan and evaluate the query this way. Okay, right. If we now perform the vacuum on the index table, then we should be back to square one. This should be the good situation again, right? So all the obsolete row versions, they would be indeed removed from the pages. The indexes would be maintained. Everything that's left on the pages is indeed visible for everyone. This would be the clean vacuum, the clean situation again. And it would be the best situation for index-only scan. So let's invest some time in the vacuum here. Performing that. All right. And now check the visibility map information. I think all the pages are present indeed there. Due to reorganization here, we now occupy even more pages, but all of them have their all visible bit set. All right, and if we now go back to the evaluation of the query, our index-only query, we will see that we are back to index-only scan with heap fetches 0, which is perfect. Okay, so that would be index-only query evaluation, which can really be key to the creation of really high-performant database applications that are evaluated inside the B+ tree only. Which is of course working best if the tables do not undergo frequent updates, or if we can invest the time for a vacuum now and then to bring everything back to its clean state. All right, so much for index-only query evaluation. This is considered to be a rather advanced indexing topic already. I think there's 2 more videos left until we can close chapter 10. I hope you stick around with us and I hope to see you there.